I've been thinking about where Earth's water came from, and what I just learned completely flipped everything I thought I knew. For years, scientists told us that asteroids brought water to Earth locked inside minerals, chemically bound into rock structures. But samples from an asteroid called Ryugu just revealed something nobody expected. Ice, preserved for over 1 billion years, hiding in plain sight. This isn't just a footnote in a textbook. This discovery means asteroids may have delivered 2 to 3 times more water than we ever imagined, enough to fill Earth's oceans 60 to 90 times over. So here's what we used to think. About 456 billion years ago, out on the edges of our solar system, asteroids formed packed with carbon and water. Scientists believed that water either evaporated quickly or got locked into hydrous minerals. Basically, water molecules chemically incorporated into the crystal structure of rocks. The story was simple. Asteroids delivered water to Earth, but it was all trapped in minerals, released slowly over time as those rocks broke down. But Ryugu samples tell a different story. Researchers led by Tsuyoshi Iizuka at the University of Tokyo discovered that Ryugu's parent asteroid kept water as ice for over 1 billion years. Not mineral-bound water, actual ice. Iizuka said, "We found that Ryugu preserved a pristine record of water activity, evidence that fluids moved through its rocks far later than we expected." Think about it this way. We thought the water was locked away immediately, but instead it stayed frozen, waiting. So what is Ryugu, and why does it matter so much? Ryugu is a near-Earth asteroid, a carbonaceous rock that's been floating around our cosmic neighborhood, carrying secrets from the solar system's birth. In 2018, Japan's Hayabusa 2 spacecraft rendezvoused with Ryugu, touched down on its surface, and collected pristine samples, untouched material from billions of years ago. Those samples made it back to Earth in 2020, and scientists have been analyzing them ever since. What they found blew the doors off our old assumptions. The parent body of Ryugu, the larger asteroid it broke off from, held onto water in ice form for more than 1 billion years. Then, something happened. Isotope dating revealed that a collision with another celestial object melted and evaporated that ice. The collision was so violent it actually distorted the age of the samples, making them appear to be 4.8 billion years old, older than the solar system itself. That distortion was the clue that something dramatic had happened to Ryugu's parent body. Okay, so how do scientists actually figure this stuff out? The answer is isotope dating. Isotopes are versions of elements with different numbers of neutrons, and they decay at predictable rates, like a cosmic clock. By measuring the ratios of certain isotopes in Ryugu's samples, researchers could determine when water last flowed through the rocks. What they discovered was shocking. Fluid activity happened way later than anyone expected, over 1 billion years after the asteroid formed. Here's what's really cool about this. The collision that distorted the dating also gave scientists a before and after snapshot. Before the impact, ice sat frozen in Ryugu's parent body. After the impact, heat from the collision melted that ice, allowing water to flow through the rock and leave chemical fingerprints. Iizuka explained, "The water hung around for a long time and was not exhausted so quickly as thought. That long-term preservation is what changes everything about our understanding of how water got to Earth." Let's talk numbers because this is where it gets wild. Under the old model, scientists estimated that carbonaceous asteroids like Ryugu delivered water locked in hydrous minerals, maybe enough for a few oceans worth. But with the addition of long-stored ice, researchers now think asteroids may have delivered 2 to 3 times more water than previously calculated. We're talking about 60 to 90 times the mass of Earth's current oceans. 60 to 90 times. Let that sink in for a second. So how does that translate to Earth's total mass? Isotope comparisons show that about 6% of Earth's matter came from asteroids like Ryugu. If those asteroids carried all that extra ice water, the total water delivered could have been up to 1.8% of Earth's entire mass. To put it another way, nearly 1/50th of our planet could be water delivered by icy asteroids. That's not a minor detail, that's a fundamental rewrite of Earth's origin story. So why does this matter for us, right here, right now? Because every glass of water you've ever drunk, every ocean wave, every raindrop, it all had to come from somewhere. If asteroids delivered vastly more water than we thought, It changes the starting conditions for Earth's entire water system. Izuka put it this way. The idea that Ryugu-like objects held onto ice for so long is remarkable. It suggests that the building blocks of Earth were far wetter than we'd imagined. This forces us to rethink the starting conditions for our planet's water system. Think about it. A wetter early Earth means different chemistry, different conditions for life to emerge, maybe even a different timeline for when our planet became habitable. The water didn't just trickle in slowly from minerals. It arrived in massive quantities as ice, melted during violent collisions, and pooled on the surface. That's a much more dynamic, chaotic picture than the slow, steady mineral release story we've been telling. It means Earth's oceans might have formed faster and been more abundant earlier than we realized. But here's the thing. This discovery opens up as many questions as it answers. If asteroids delivered up to 90 times the mass of our current oceans, where did all that extra water go? Some of it probably escaped into space during Earth's violent formation, blasted away by solar wind and impacts. Some of it might be locked deep in Earth's mantle and core, hidden from view. And some of it, of course, is right here on the surface. Our oceans, our ice caps, the water in your body. Izuka and his team are now working to figure out the balance. How much escaped, how much stayed hidden, and how much became the life-giving surface water we depend on. He said, "Though it's too early to say for sure, my team and others might build on this research to clarify things, including how and when our Earth became habitable. That's the next frontier, tracing the journey of ancient asteroid ice through billions of years to the water we see today." So that's where we are. A single asteroid's samples have forced us to rethink the starting conditions for our planet's entire water system. Ice preserved for over 1 billion years, delivered in quantities far greater than we imagined, shaping the world we live in today. The mystery of where all that water ended up is still being solved, but one thing is clear. Earth's oceans have a far more dramatic origin story than we ever knew. I'll be keeping an eye on what comes next. And I think you should too.